A transformation matrix is simply a matrix that tells us how a function or a set of functions changes when we apply a symmetry operation. When a symmetry operation acts on a set of functions, it transforms them into linear combinations of each other. Suppose we have a set that consists of some basis functions. For example, take the three functions x, y, z. Now apply a symmetry operation, say a C4 rotation about the z-axis, and see how these function changes. It is important to note that we have included the sign of the axis in our basis function. Here we are studying the transformation of a group containing three different functions. Mathematically, we can represent the operation using a matrix form. Let's say, after the C4 operation, the new set is x prime, y prime and z prime. Then how the new set is related with the x, y, z can be determined by a suitable matrix. If we observe the C4 operation on x, y, z, then we will find x is moved to the y becomes minus x and z remains unchanged. Here, by observing the changes, we can design a matrix which can explain how individual x, y, and z transforms. In this case, C4 acts on x, y, z to form x prime, y prime and z prime, which is y minus x, z. Here, the C4 matrix can be easily evaluated by using simple matrix multiplication. The C4 matrix for x, y, z is this. The size of the matrix depends on the number of functions that we observe. It can be one-dimensional or multidimensional. If we consider only one function, let's say x, then the matrix will have only one element. We will call it one-dimensional matrix. For example, if x is a function which is closed under operation, let's say O, and it transforms it into ax after the operation, then the matrix will contain only one element, that is A. If we have two functions, such as x and y, then the matrix associated with the symmetry element will be two-dimensional. Here we are observing the changes for x and y. If after the symmetry operation, x becomes ax plus by, y becomes cx plus dy, then the transformation matrix will look like this. Here there are two rows and two columns. Here, it is important to note that among all the elements of a multidimensional matrix like A, B, C, and D, A and D carry significant information. These are called the diagonal elements. In this example, if we say after the symmetry operation, the new x, which is x prime, is a linear combination of x and y, such as ax plus by. Here, if we want to know what is the contribution of x in this new transformation x prime, then the answer will be A. Although, B also contributes to the new function x prime, but it carries the information for y. Similarly, for y prime, which is cx plus dy, only D tells the contribution of y in y prime. So if we consider the diagonal elements of a matrix, we can say how the original function is contributing to the new function. This is the example of two-dimensional matrix. Similarly, if we increase the number of functions, the dimension of matrix will increase. For example, if we have 5 different functions, then we will have a 5-dimensional matrix with 5 rows and 5 columns. And all the diagonal elements will be used to understand the contribution of a particular function in its new function. Here, the sum of the diagonal elements of the matrix is called the trace of the matrix. This is what we call the character of a particular symmetry element for a particular set of functions. Now coming to a real example, Suppose we want to analyze the transformation of 5D orbitals under a symmetry operation, let's say C4 axis. Here we have 5 functions. So the matrix of C4 must be 5-dimensional, that means 5 rows and 5 columns. First, we will observe physically how the functions change in the presence of the C4 axis. And based on their change, we will fill the character of the 5-dimensional matrix with the C4 operation along the z-axis. xy becomes minus xy. yz becomes minus xz. xz becomes yz. x square minus y square becomes minus x square minus y square. And z square remains the same z square. The matrix will now look like this. If we multiply the functions by this matrix, then we will get the new functions. Here if we look at the diagonal elements, in the first row, which is related to the first function xy, is minus 1. It indicates the function xy changes to xy with a change in sign. That also indicates xy contributes fully in the new function minus xy. In the second row, which is associated with the second function yz, the diagonal element is 0. It is because the corresponding function, yz, is completely transformed into minus xz. So it has 0 contribution in the new function. Similarly, for xz it is 0. And for x square minus y square it is minus 1. And since z square remains as z square, after the operation, the character of the diagonal element is 1. And here it is fully contributing to the new function. Here the trace of the matrix is minus 1. This is the reducible character of the C4 axis for the 5D orbitals. This we will discuss in our subsequent videos.